I'm going to look at just that third page, and I'm going to make these really big. So normally if we were to use direct substitution, could I use that here? Yes or no? No, because x cannot be 0. So you're going to learn to use your properties. So if you look at the properties at the very front of your notes, we can add, subtract, multiply, and divide limits and split them apart and just add, subtract, multiply, and divide them. So that's kind of what we're going to do today, using one very important fact. We're going to use, well, let's go ahead and split this first one apart. So if I can't use direct substitution, one of our tools is to take this one fraction and split it into two separate fractions. So what are the two fractions that I could split this into? Come on, what are my two fractions? X over x, right? And then plus sine of x over x. So that's where we're going to start. So equals the limit as x approaches 0 of x over x plus, because there's a plus between the x and the sine of x over x. So then we're going to find the limits, whoops, I didn't want that. We're going to find the limits of each of these separately, because those properties on the front of your note says that I can find the limit of this and the limit of this and then just add them together. And so we're going to split the limits up. Notice I haven't found the limits yet, so I'm not dropping the limits off. So I have the limit as x approaches 0 of, what is x divided by x? 1. So can't I just replace that with 1? And then plus the limit as x approaches 0 of the sine of x over x. So let's talk about each of these limits separately. What is the limit of any constant? Remember, this is a graph of y equals 1. So as x approaches any number, it doesn't matter, it's approaching 0. As x approaches any number, what's the y value on this horizontal line going through the y-axis at 1? What's always the y value? Y equals 1. Well, go over here. Go over to your calculator and put into y equals 1 and hit graph. So as x approaches any number, not just 0, what's the y value? 1. So what if I change this to, oh jeepers, it's going to do it to me again, isn't it? Maybe I won't buy the TA Smart View because it keeps pooping out on me. There it goes. Reopen. Patience is a virtue, and I don't have it. Yeah, no, I only have one free day left. Thank you. Okay. So what if I put here instead 10? Graph. What's the limit as x approaches 7?
7.
Nope. What's the limit as x approaches 7? So here's 7 somewhere around here. What's this height? 10. What's the limit as x approaches -2? 10. So it doesn't matter what x is approaching. When you have a constant, the limit is always that constant. So in our case, it was 1. All right, so then over here, can't I replace the limit as x approaches 0 of 1? Can I replace that whole limit with 1 as a value of 1? Then plus, now we're going to find the limit as x approaches 0 of sine of x over x. So go to your calculator. Make sure that your mode on your calculator is in radian mode. If it's in degrees, it's not going to graph it correctly. So start there. Then we're going to go to y equals. We're going to clear that out. And we're going to put in just the sine of x, close your parentheses, divided by x. And we're going to graph. And we have a little hill right here. So I am going to zoom in once on this, just so you can get a better picture of what's going on. And there we go. So as x approaches 0 with the sine of x over x, as x approaches 0 from the left, what's the limit? 1. And from the right, what's the limit? 1. There technically is a hole in the graph right here because x cannot be 0, but that doesn't matter. The limit as x approaches 0 from either side is 1. So that tells us that this limit here isn't at 1. So this entire limit you're going to get used to. We're going to do that over and over and over again. And so you're going to see your textbook is going to tell you, using the knowledge that the limit as x approaches 0 of sine of x over x is 1, you evaluate the following. Well, I'm not going to tell you that because by the time we've done it in our notes and by the time you've done your homework problems, you should know what the limit of sine of x over x is because you've done it so many times. It's just like you'll start to learn what the limit is as x approaches 0 of 1 over x. You'll start to understand what that limit is, and you don't have to plug it into your calculator and look at the graph anymore. Okay? All right, so what's 1 plus 1? How is it toughy? It's 2, right? So the entire limit is 2. If I were to put the original equation on my calculator as you were taught on Friday, so I'm going to clear that out, and I'm going to use parentheses, and I've got x plus the sine of x, n parentheses again, divided by x. So that's what we started with, right? And if we were to graph that, notice where the limit is going this time as x approaches 0. What's that limit? 2. And isn't that what we came up with partially algebraically? All right, so the joy is that we can start to use our algebra to shorten up our work. So it's a lot less work to just use the algebra rather than graph it. So let's look at B. So again, for B, can I use direct substitution? Nope. But this one's interesting. I mean, I could split it into 1 over x squared minus cosine squared x over x squared. But you'd have to graph the 1 over x squared to see what that limit was. And you'd have to graph the cosine squared x over x squared and see what that limit was. And you'd have to subtract them. This should be a familiar item to you. This right here should be real familiar. We've seen that in the past. Correct. Can't we replace that with sine squared? Isn't that a Pythagorean identity? Oh, yeah. Do we have to know those, Mrs. Murray? Absolutely. Mastered a test with them on there. So for this one, we're going to change it to the limit as x approaches 0. And instead of that numerator, we're going to replace the numerator with sine squared of x all over x squared. And so now we've got a sine of x in the numerator and an x in the denominator. I can actually split that up to where it looks like the limit as x approaches 0 of the sine of x over x times the sine of x over x. Wouldn't you agree that these two multiplied together gives me the same fraction here? Right? And so I can find the limit of this and multiply it to the limit of this. So I haven't found the limits yet, and so you cannot drop the limits off. And so some of you who are skipping some of these steps, we're going to miss it on your test. And you're going to lose points. But why? I got the right answer. It's not about that. Calculus you have to prove as you go along. So what are each of these limits here? Yeah, we just found that they're 1. So we're going to replace those values with 1 times 1, which gives us a value of 1. And so again, if you had put that original function right here into your calculator, you should see as you approach 0 the limit being 1. But you'll find that this gets really, really quick when all is said and done. It's a lot quicker than graphing. All right, C. C is dealing with roots. And so watch the progression of your roots as we go along. So So if both of these have the same roots, that means I can rewrite this till it looks like this. I can put them both underneath the same root. And why would I want to do that? Why would I want to put them both under the same root? Because you got that sine of x over x in there, right? And that's what we're working with. Now, technically, we've got to take this cube root and we've got to take this right here does not have a value of 1. Its limit does. So we'll take the cube root of the limit. So it technically has to be written as the cube root of the limit as x approaches 0 of the sine of x over x. That cube root comes out in front. You're actually taking the limit of the sine of x over x, which is what? What's that limit? What's the limit of what's underneath the root? 1. So we're taking the cube root of 1, which is 1. So actually, when I physically take the limit, that's when the limit notation drops off. Questions on that before we go to the next example? We all good? Do this again, what I just did? Whoops. So all I did was take the original function right here. They both have the same root. And so I took them and put them both underneath the same root because algebra says that I can do that. And then I can take this root and I can actually put it outside the limit, if you will, and then just take the limit of this underneath and then finally take that cube root. And that's really what I'm doing. I don't have a value on this, but I can take its limit. And so I took the limit of that function first before I took the cube root. And then once I had the limit of that function here, then I took the cube root. And our properties on our other page say I can do that. All right, so let's look at the next example. So we're back to limits by substitution, but these are a little bit more difficult limits. We've got sines and cosines and tangents in there and so forth. So let's go ahead and look at this first one. So I've got the limit as x approaches. Can I use direct substitution here? Is there any issue with it in the denominator? Yes or no? Yes or no? Yes? Is the cosine squared of 0, is that going to give me a 0 value in the denominator? Well, let's look. Let's go ahead and put our substitution in. So e to the 0 minus the tan of 0, all divided by cosine squared of 0. So go back to your unit circle. And at 0 radians, which is right here, what is the ordered pair?
It's 1, 0.
Is it 1, 0? Yeah, you have to really think about those. It is 1, 0. And then cosine is your x value, sine is your y value. But we want tangent also. So tangent is equal to sine over cosine. So in this case, my sine is 0, my cosine is 1. What is that value? Is that a value of 0 in the numerator? Yes or no? Yes, it has a value of 0. So I can actually plug those values in because at my denominator is cosine squared at 0. Well, at 0, cosine is 1. So here's what we end up having. So what's e to the 0? 1 minus what's tangent at 0? 0 right there. All divided by cosine at 0 was 1, but it's squared. So we've got 1 squared, which is 1 over 1, which is 1. So using our algebra gives us a more exact answer. You okay with that? What if the tangent had been in the denominator squared and the cosine had been in the numerator? Would we have been able to do it this way? No, because the tangent zeroed at 0. So that would have been an undefined. All right, so let's review logs. So I can use direct substitution again because I can take the log base 2 of 16. So let's look to see what all that looks like. So I've got the limit as x approaches 16 of the square root of 16 divided by the log base 2 of 16. So that's easy enough. I've got, I'm actually using direct substitution so I can drop off that limit. What's the square root of 16? 4 over, and then before I find the log base 2 of 16, let's write 16 in its exponential form, because if I have this base of 2, can I write this as a power with a base of 2? And why would I want to do that? Because the 2 and a base of 2 here, they're going to cancel each other out, and whatever my exponent is, that's going to be my answer. And so it looks like the log base 2 of 2 to the 4th. And so the fact that those two are the same cancels out that log, if you will recall, and we get 4 over 4, which has a limit of 1, overall limit of 1. Any questions on that before we do the very last one? Yes?
I'm still kind of confused when you put the limit, like x to 16, like when and when you don't, because like with the last two steps.
When I drop off the limit?
Yeah.
When I actually use direct substitution. So technically here I could have dropped off the limit. I just didn't. But you definitely don't want to drop it off too early, which a lot of you are doing. Okay, so then look at the last one. The last one is a piecewise function. Okay. So before I can do this, I'm finding, what is this asking me to find? What's this right here asking me to find?
Left side.
The left-hand limit, right? Correct? And this one's asking me to find the right-hand limit. And then the function is this whole big ugly thing here, which is a piecewise function. So we need to graph that function. Notice that the number that we're approaching 2 is our boundary point here at 2. And so that's going to be important, that this is our left-hand side, and that this is our right-hand side because this is greater than. And so we're going to go ahead and graph this, and you're going to use your calculator to help you with your graphing. And because we're not using graph paper, make sure that you're pretty accurate with your hash marks. Obviously, I can't use straight lines here, so mine's not going to be as pretty as it could be. Okay, so I'm going to put into my calculator the parabola right here, this negative x squared. Be careful when you put it in here. I'm going to go back to my Zoom standard. So I have a normal viewing window. And then I'm going to go to y equals, clear that out, and put in my negative x squared. Use the negative, not the subtraction button. Then plus 4x and minus 1. So here's our parabola. Whether or not your vertex is on that boundary line, if the boundary line is x equals 2, you want to make sure you find the vertex of that parabola. It helps you get the shape of the curve. So how do I find the vertex of this parabola here? Trace does not always give you an accurate answer.
The maximum.
How do I get to the maximum? Second calc. And then I want to choose the maximum, so I want to choose 4. If it were a parabola opening up, I would have chosen the minimum. And so it's asking right bound. I like to get it just a little closer to my vertex. So enter. And then you have to move it to the right of your vertex. And then enter. Oh. Okay, all right. It didn't like that. Let's try one more time. second calc, 4 for my max. I want my left, so enter. I want my right, hit enter. Aha, I don't know what I hit before. All right, so an interesting thing occurs on this one. Sometimes this happens, right? What is my x value really? It's really 2, especially if you go into second graph and look at your table of values. If you put in 2, don't I get a 3? So over here, what I would like you to do is I want you to plot in this boundary line right here at x equals 2. So we're going to put that in. I'm going to put that in as a red dashed line. So you should use a straight edge. I can't, but you can. So this is my boundary line. It's not really part of my graph, but that's the right and the left side that I'm finding the limit to. And so we're going to plot the ordered pair right here at 2, 3. So it's right here. Is that going to be an open circle or a closed circle if x is less than or equal to 2? So open or closed?
Closed.
Closed circle. So this open circle right here becomes a closed circle. And then go ahead and use your, I'm going to move this to the right so we can kind of see my graph. Use your table of values to your advantage. So we already put in 2. What's a number to the left? Because I want to be graphing to the left here. So no, well, don't go quite so far. So I want to go, the first number to the left, isn't it 1? So I want to plug in 1. And I get 2. So I'm going to plot the point 1, 2. And then my next number to the left is 0. So I'm going to put in 0. And I get a negative 1. I'm going to do one more, would be negative 1. So I'm going to put in negative 1, and I get negative 6. And all that does is it allows me to have a shape to that parabola. And then I'm going to graph the right-hand side. So I'm going to graph the 2x minus 3. So I'm going to go to my calculator, go to y equals. Clear that out and put in 2x minus 3. And hit graph. I really don't care about the graph because I'm going to use my table of values. What do I want to make sure that I plug into my table of values first? What's the very first number I want to plug in? Not 3. Don't I want to plug in my boundary point? Even though it says less than 2, I still have to know where it crosses at 2. So I do have a value in here at 2 already from the previous one that we did. So 2 is at 1. So at 2, 1, I have a point here. Is that an open or a closed circle? It is open, and I have to put that in there. So I have an open circle. And then I'm going to start to choose values to the right. So I now want to put in 3. And so 3 gives me a value of 3. So I'm going to plot 3, 3. And then I'm going to put in 4. And so that gives me 4, 5. And I think that'll be good enough for this. And connect the dots. And then make sure that you are labeling your lines. And move this back over now. So label your lines. This is y equals 2x minus 3. And this is y equals negative x squared plus 4x minus 1. So now we can actually answer the questions that they want. And the questions that they're looking for is what is the limit as x approaches 2 from the left. So we're going to find that limit. Of f of x is equal to. So as I approach 2 from the left, what is happening to my y value? If I approach from the left, what's happening to the y? What value does it come closer and closer to? It's like riding a roller coaster up there. You get a value of not 2, but What's that y value? 3. So the limit as we approach 2 from the left has a value of 3. That's the y value. But notice what the limit is as we approach 2 from the right side. So as I approach 2 from the right side, what's happening? We go from here down to what number? Not 2 again. Think y value. So as I approach 2 from the left, the y value is getting closer and closer and closer to positive 1. It doesn't matter that there's a closed circle up there. To the right of 2, the value of y gets closer and closer to positive 1. And so that's our right-hand limit. So then what is the limit as x approaches just 2? Does the left and the right-hand limit agree? Nope. So mean girls say the limit does not exist. If the right hand and the left hand limits do not agree, the limit does not exist when x is approaching 2. It exists everywhere else on this graph, but it doesn't exist at that boundary point of x equals 2, and so does not exist. And your Math Excel book is calling this undefined. Most textbooks are going to say does not exist. Yes?
Can you explain how you got 3 and 1?
So you want to be looking at the graph as you approach from the left and the right. So as I approach from the left and the right, look at what's happening with the graph. So this is coming from the left. Notice the x value is getting bigger and bigger and bigger. So I'm approaching 2 from the left. And look at what's happening to the y value. It's getting bigger and bigger and bigger until it actually is 3 at 2. Okay, so that's where the 3 comes from. On the other side, you can always take the graph and just follow the graph to where the x value is that you're looking for. So as I come from the left, here's the graph. I'm following it, following it, following it until I hit this point, which has a y value of 1, even though it's an open circle. As I come to the right of 2 here and get closer and closer to 2, that y value is getting smaller and smaller and smaller, and it's approaching 1. It doesn't ever become 1 because of that open circle, but it does approach 1. And because the left and the right hand limits do not agree, the overall limit at 2 does not exist. There's a limit everywhere else, just not at this point. And at this point right here, at x equals 2, so you're going to want to write this. X equals 2 is a point of discontinuity. This is going to bring us into our discussion for tomorrow, but x equals 2 is a point of discontinuity, and the reason for that is you see this jump. There's a break in the graph. It is possible that this right here, this open circle, could have overlapped here, and then we could have had a straight line going off from here, and then you would not have had a point of discontinuity. And then your left and right hand limits would have agreed, and you would have had a limit that existed. But because this side bops down here to this open circle, you have this jump, this gap in the graph, and that's this point of discontinuity. And we will talk about that tomorrow along with limits at infinity. Are there any other questions before we stop? Okay.